Hello, dear colleagues. I am Vicente Matus from IDETIC, Universidad de Las Palmas de Gran Canaria. Today I'm going to present our work on the wireless sensor networks using sub-pixel optical camera communications, advances in experimental channel evaluation. In this work, we show several studies of the influence of the outdoor scenario to optical camera communications in the context of wireless sensor networking. For this purpose, a group of experimental setups have been tested in real and emulated conditions of meteorological phenomena, of heat-induced turbulence and the presence of fog in an atmospheric chamber, and conditions of heavy storm in real outdoor scenario. The outcome of these experiments is a proposal of a capable architecture of optical camera communications that can be used in wireless sensor networks, that assures a low cost of implementation and the possibility of escalating the amount of connected devices to hundreds of them in a field of dimensions of 100 by 100 meters approximately. The following parts of this presentation are structured as follows. First, we introduce the concept of rolling shutter optical camera communications and some issues found in their real implementations. Then we show the optical wireless communications devices employed in our experiments. We then review the experiments done in different scenarios and atmospherical conditions, and we show the proposal of a wireless sensor network using optical camera communications, which falls in the category of sub-pixel optical camera communications. To finish our presentation, giving some conclusions of our work. Optical camera communications, or OCC, are usually implemented using complementary metal oxide semiconductor, or CMOS cameras, due to their low cost and availability in the market, since they are the main technology among portable devices such as smartphones. The CMOS cameras scan the sensor row by row, having a slight delay on each line. This mechanism allows the OCC receivers to capture more than one state of a blinking lamp, and thus capture different values of information in one single frame. The image in the center, showing the output from the camera, depicts the rolling shutter effect, where the blinking light is translated into an image with black and white horizontal stripes. In real outdoor scenario, OCC will face the presence of uncontrollable atmospheric conditions and the interfering light from sources such as the sun and public luminaries. The implementation of OCC in outdoor then has issues such as the need of having large sources and large optics to ensure a considerable projection of the lamp into the frame. This induces another issue, that the camera itself cannot be used for monitoring or as photographic device, since most of its field of view is taken by the transmitting lamp. We have developed a family of optical devices using visible light communications, based on LED lights in the case of the transmitters and CMOS cameras in the case of the receivers. The devices developed differ from the size of their optical end. Small lamps' dimensions are 5 mm diameter and large ones are around 50 centimeters long. Small cameras use microlens array of 1 mm diameter and big cameras use 70 mm long telescope. Our first experiments were carried out using a laboratory chamber, capable of emulating the presence of fog and heat-induced turbulence. This experiment showed that the camera analog gain can be used to improve the signal-to-noise ratio, or SNR, of the communication. We then experimented in real sandstorm conditions, using large transmitters and receivers, achieving 200 meters communication of around 2 kilobits per second. The sandstorm attenuation was overcame using analog gain of the camera, along with the large optical devices employed. Finally, the small devices were deployed in an open field, at distances of 90 meters and 130 meters, and thus the projection of the transmitters over the image is smaller than the area of one pixel, falling into the category of sub-pixel OCC, not to be confused with the concept of subpixels underlying the circuitry of the red, green, and blue image sensors. The subpixel OCC addresses the issue of reutilizing the cameras for both photographic or monitoring purposes and the communication functionality with the same camera, because the transmission occurs in a negligible amount of the area of the image. In the video, we show the real image frames captured with our small CMOS receiver. The photographic monitoring of the field is possible simultaneous to the download of data from the two nodes. If we zoom into the pixels around the projection of the transmitters, we can see the signal received with an SNR of about 17 decibel. The image shows an actual area of pixels with data, because although the projection is sub-pixel, the scattering of the atmosphere and the focus of the camera cause the rays to impinge more pixels. We can now propose a sub-pixel OCC-based wireless sensor network, in which simple nodes including the sensing part, a battery, and an LED, compute by a microcontroller, can send simultaneous information to the camera about 100 meters away. The camera can process the data along with the image acquisition, or it can just send the video to a cloud service. This system would allow several hundred nodes connected to a single camera, with a data rate of about 7 bits per second for each device, according to our experimental results. The potential applications of these kinds of setups would be, for example, in precision farming, where soil moisture, temperature, and water control need to be monitored from different points of the field in order to make maps of the resource management. In this work, we have shown how OCC can be used as a technology for sensor networking. We have experimentally tested rolling shutter OCC systems in emulated and real conditions, characterizing outdoor phenomena such as sandstorms, the effects of fog, and turbulence. We have introduced the concept of sub-pixel OCC for applications in which a video for monitoring could include the download of data from nodes placed in the field of view. With this, we have proposed a wireless sensor network but based on the sub-pixel architecture. We thank our funding institutions and we thank all of you for attending this presentation. We are willing to collaborate. Please contact us, and thanks for your attention. Goodbye.